There we go.
All right, perfect. Let me just make sure I grab the right version of the slides. One
Completely
sec.
understand.
I have too many windows open on my desktop right now. I'm sorry. All right, there we go. And let's do this. And where does Zoom go? All right, so oops, one second. Let me do it this way. Sorry.
Congratulations, your last plan.
All right, so now you should see my slides. Cool. All right. Hey everyone, how's it going? I'm Rob Zellem. Actually, these are the wrong slides again. Sorry. So basically, I'm here to talk to you about Exoplanet Watch, a citizen science project to observe transiting exoplanets. So those of you who don't know, an exoplanet is any planet outside of our own solar system. Usually they're orbiting other stars, but there are some exoplanets out there that actually are called rogue planets or free-floating planets that just sort of are
Rob, are you
floating out
sharing your
there.
screen? Sorry to interrupt. There
No,
we
there
go.
you go.
Sorry.
No worries. Filling in the time I was finding the right thing to share. Okay, cool.
Okay.
So what we're doing at Exoplanet Watch is the citizen science project to actually have any of you help us observe these exoplanets from the ground using small ground-based telescopes. And what you'll be doing is you'll be helping us really give back to NASA missions. So in this talk, I'll be giving a quick overview of our project Exoplanet Watch, what we launched actually about a year and a half ago. Um, it's a citizen science project to monitor transiting exoplanets, and we've been really developing this project since 2021, so about last 4 or 5 years now. So we've been doing a lot of work on it. But one thing I'm really proud about for this project is that anyone and everyone can participate in it. And you can, by you're participating in the project, you can learn how exoplanet science is really done, just like other amazing citizen science projects like Kilonova Catcher as well. So some quick background. A transit is when, if you're looking at a host star, if you're really lucky, that star has a planet around it. And if you're even luckier, that planet will pass in front of the star, causing the star to appear to dim. And the amount of light that it blocks out is basically shows you how big the planet is relative to the star. So the bigger the planet, the more light it'll block out. You'll get a bigger dip in brightness of the host star. So we can actually measure the radii or the areas of these exoplanets relative to their host star. The transit method is also used a lot by professional astronomers to measure the atmospheres of these planets as well. So when a planet passes in front of the star, not only does the optically thick portion of the planet's disk block out the star's light, but also the very thin annulus of atmosphere. And that atmosphere will absorb the host star's light differently at different wavelengths, depending on the molecules in the atmosphere of that planet. So you can use transits to actually characterize the atmospheres of these exoplanets. And by participating in Exoplanet Watch, you can actually help us refine these transit times so that we can then use James Webb, Hubble, Ariel, a European Space Agency mission that's launching at the end of this decade. You can help us give more accurate times when these transits were to occur for these missions and others as well. So if you want to observe a transit with any of these missions, Hubble, James Webb, Ariel, Pandora, anything else, you need to know very precisely when that transit event occurs. Otherwise, if there's like a 15-minute uncertainty in that upcoming time, that's additional overhead you have to build into your observing campaign. And that translates to wasted time. We're using these telescopes as a result less efficiently and less effectively. But what we found is that small ground-based telescopes can help us observe these transits from the ground, and then they will enable us, by looking at transits today, better predict when the next transit event were to occur in the future, so we can use these precious resources a lot more efficiently and hopefully expand their science capabilities. So this need is what caused us to launch Exoplanet Watch, a citizen science transiting exoplanet mission project. And in this project, we have folks routinely observing these transit exoplanets to keep their transit times precise. And by doing so, you'll directly and help enable NASA science. And to date, we've actually saved a few hours of James Webb time worth hundreds of thousands of dollars. Exoplanet Watch, we're a completely collaborative effort to complement existing surveys. All of our data is immediately public. You can go on our website right now and get any of our data or data products. You can use it for your own research or analysis as well. There's no proprietary phase to our data, so everything is completely open science, open data. We also have target requests by professional astronomers. For example, we are collaborating with the Pandora mission. I'll be talking about that a little bit later in this talk. This is a NASA smallsat that's being led out of here by NASA Goddard. And Exoplanet Watch users are helping to enhance the science returns and capabilities of Pandora by getting longer baseline measurements of exoplanet host stars. Also, all of our observers are listed as co-authors on our papers. If you do the work, you deserve the credit. This is something I'm very passionate about, and luckily, it's been amazing to have tons of amateur astronomers and citizen scientists on our papers. And we're funded for a bit by NASA's Universe of Learning. So as a citizen science project, we have educational goals and science goals. So the science goals I've sort of already talked about. It's really to ensure the efficient use of large telescopes. We're also starting to get into the planet discovery and confirmation phase by following up on planets that have candidates really that have been discovered by other NASA efforts, such as NASA's TESS mission. And we're beginning to monitor for stellar variability, which I'll talk about a little bit later as well, to help enhance the science returns of various NASA missions and goals. For our educational goals, though, is to engage and teach the public about exoplanets to enable them to do science. And really, at the end of the day, it's to help inspire that next generation of people to perhaps pursue astronomy or another STEM related field. And we've been lucky enough where we've actually had folks in high school or secondary school who have been participating in Exoplanet Watch, and now they're getting their degrees, undergraduate degrees in astronomy, which is pretty incredible. So if you're interested in helping us out on Exoplanet Watch, here is your basic user experience. It's a little overwhelming at first, but I'll step through it line by line, so don't worry about it. If you are on the line and you're lucky enough to have your own telescope, you can actually go on our website and we have a little plugin in there through our friends at the Swarthmore Transit Finder, where you can enter your location on the Earth and it'll tell you exactly what planets are visible from your neck of the woods on any given night. And there's at least tens of targets that you could observe any given night. Then, just like Brian Martin here, one of our exoplanet watchers, you can use your awesome telescope to help us observe these transit events. We have people with telescopes as small as 2.5 inches. That's only a few centimeters big, I think about 6 centimeters wide, who have been able to help us and been contributing science grade observations to this project. If you're like me and you don't have a telescope, or if you live in a light polluted area, I live just outside of Washington, D.C., out here in the US. It's typically cloudy, and also I don't have a telescope. You can actually request data from us. Our friends at the Micro Observatory, run out of Harvard CFA, have very kindly donated over a decade's worth of data. So thousands of data sets that they've donated to us so that anyone who has an internet connection and a smartphone can participate fully in this project. And we need your help to help us run through and analyze all this micro observatory data. Then once you have your data, either through yourself, your own telescope, or through us, you then perform the data analysis yourself. You can use whatever analysis tool that you want. Tons of folks out there use Astro Image J. It's a very popular one. We also have our own homegrown one called Exotic. I'll talk about in a second. But you actually perform the full data analysis yourself. Then you contribute your observations, you upload them to the American Association of Variable Star Observers. They have an exoplanet database that they're very kindly letting us and our users use completely for free. And this is how we sort of gather all the data together. And then our pipeline goes and reaches out and scrapes that data every few days to then update our database and publish it to our website. Then after that, you sort of sit back and relax, and hopefully you get published. Or you can also publish your own papers using any of our data or data products. The only three things that we ask is if that you're publishing someone's data for the first time, that you reach out to them and offer to make them a co-author, because again, if they do the work, they deserve the credit. Or in addition, please cite one of our papers. There's actually two we recommend now, and then also give us an acknowledgement. So pretty low bar for entry for using our data or our data products, all of which are immediately public to anyone out there in the world. So I briefly mentioned Exotic. This is our exoplanet transit interpretation code. And this is a real astronomy analysis tool. This is literally the same exact code that I use as a professional exoplanet astronomer myself, but we've just made the front end of the user experience a bit more user friendly. It runs completely either on your computer, but what we really recommend people do is they run it on the Google Colab Cloud. So rather than running any software or doing any installation locally on your own machine, you instead run everything on free Google servers. So you don't have to download anything, you don't have to worry about installing anything. And the great thing is that you can run it completely from your smartphone. So I've actually analyzed Exoplanet Watch data from my smartphone, or folks can also use their Chromebooks. So you don't need a fancy, fast computer to participate in this project. But all the code in the back end, underneath the surface, is all the same code that we use as professional astronomers, or that I use for my own studies as well. So what this does, this teaches you exactly how science is done because you're actually doing the data analysis yourself. And online, we have step-by-step tutorials, including videos on how to use it. We also have a very friendly Slack channel as well, where you can learn and get help from all of our users in real time. So another example of where we've been helping out with observing is that back in December 2021, we had this big observing campaign to help with some James Webb Space Telescope observations. Uh, this target had a multi-hour uncertainty of when the transit event would occur. Unfortunately, though, the transit took over 12 hours to observe. So when you're doing these observations, you not only need to look at when the planet passes in front of the star, causing the star to appear to dim, you also need some out of transit baseline to help you better remove errors from your data set. So all in all, we're looking at easily a 14, 16, 18-hour end-to-end observation. So it's literally impossible for any single person in the world to observe this full entire transit event. So what we did is we activated our membership base and we were able to get 24 facilities spanning the globe with all relatively small telescopes, less than zero point 0.7 meters. Most of them, though, were those 2.5-inch or 6 centimeter telescopes. And we had those folks distributed across the Northern Hemisphere. And we basically simulated a single large Earth spanning telescope that was able to observe. And we had one person after the next hand off the data and the observations to the next person to the next person again until we stitched all the data together to make this amazing light curve. So we had 24 facilities. We probably had another 30 or 40 that wanted to participate. Unfortunately, though, I believe that clouds are sentient creatures and the weather knows when you're trying to observe. Most of the northern hemisphere was completely clouded out this evening. So we had a bunch of folks who wanted to participate in the eastern coast of the United States, for example, or in Western Europe that couldn't because of cloud cover. So this worldwide distributed network does really two things. It allows us to observe these longer term events, but also they help us mitigate the impacts of weather. For example, this campaign right here. So one thing we're also working on right now is a mission called Pandora. Let me share my screen on that again. And this is what we're really focusing on for these next few months, to about the year and a half. This is a small set mission where we're trying to basically understand how a star, its activity, its spots, its plages, its flares can alter or pollute the signal of the planet orbiting around it. So this leverages the transit method, as I talked about earlier. We've already talked about the transit method right here, but basically this method is extremely important because it allows us to study these exoplanetary atmospheres. A lot of these transiting planets have been discovered by efforts on the ground, but also in space, such as by NASA's TESS mission, the Transiting Exoplanet Survey Satellite. This is a picture of the TESS mission. It's an all-sky survey aiming to discover tens, if not hundreds of thousands of new exoplanets. And it has these four onboard cameras that sort of sweep across the sky to observe these transiting events. And discovering more transit events and more planets is crucial because it gives us a larger population of planets that we can pick the best of the best, the cream of the crop, to then follow up in detail using the transit method with other space-based observatories. So the Hubble Space Telescope, for example, has used the transit method to characterize the atmosphere of about 50 to 60 exoplanets. Similarly, James Webb has been doing incredible work by using the transit method to discover, really to understand the atmospheres of, I think, about 20 or 30 exoplanets to date. And James Webb might observe about 200 of them over its mission lifetime, if not more. This fall in October of 2025, I think that's what we're on launch for right now, is NASA's Pandora mission. This is about the size of an oven, so an appliance in your kitchen. And I'll talk about this in a minute, but we're using the transit method to understand the atmospheres of about 40 exoplanets. NASA's Goddard Space Flight Center is building right now the Roman Space Telescope. This is NASA's next flagship astrophysics mission. It's actually being built right down the road from me here at NASA Goddard. And this mission will be launching as soon as next fall, but no later than May of 2027. And Roman will be discovering tens, if not hundreds of thousands of exoplanets and microlensing planets itself. Looking a little bit farther into the future, Europe, the European Space Agency, is building a mission right now called Ariel. Ariel is an exoplanet dedicated mission. I'll be launching at the end of this decade. That I'll be looking into the atmospheres of about 1,000 planets to characterize their atmospheres, to put those James Webb and Hubble observations and discoveries into a larger statistical significant context. And then even beyond that, NASA's Habitable Worlds Observatory. This is NASA's next flagship mission that'll hopefully be launching in about 15 to 20 years from now. It will likely be using the transit method as well to characterize exoplanetary atmospheres. So what this slide should really, the main takeaway is that we're basically living in this golden age of exoplanetary science. We've very quickly in the last 20, 25 years, we've gone from discovering the first exoplanet to now characterizing them, and it's sort of becoming a routine to atmospherically characterize them to the point we'll have hundreds, if not 1,000 or more by the end of this decade. And then we'll be using observatories like Habitable Worlds to look for potential signatures of life in their atmosphere. So let me talk a little bit about the Pandora mission. This is a half-meter diameter telescope. We have a 1-year prime mission, and we'll be observing at least 20 and potentially 40 or more known exoplanets of all sizes and their host stars. And Pandora will be operating at visible and near-infrared wavelengths, so about zero point 0.5 to 2.3 microns. So in light, very similar to what our eyes can see, but also near-infrared wavelengths as well. Pandora will be launching into a low Earth orbit, a sun synchronous orbit, where it sort of just orbits directly over the top of the Earth's terminator. And we have a fall 2025 launch readiness date, and hopefully we'll be launching around then as well. One of the main science drivers here at Pandora is observing planetary atmospheres and better understanding sources of error that can change our interpretation of these atmospheres. So when a planet passes in front of a host star, the planet's atmosphere will absorb the star's light differently at different wavelengths. So at 2.3 microns, for example, the planet might be more efficient at absorbing that wavelength of light. So the planet might look a little bit bigger. Whereas at 1.8 or 2.1 microns, the planet might be less efficient at absorbing that light, so it might look a little bit smaller effectively. And by piecing this information together, we can measure the spectrum of the planet, how the planet absorbs light as a function of wavelength. And then from that, we can then back out the molecules in that planet's atmosphere. And we can say that planet has methane or carbon dioxide or carbon monoxide in its atmosphere. However, there is an issue with if the star itself is spotted. Star spots, unfortunately, can mimic planetary signals, but also a star can alter the observed planetary signal as well. When we're making these transit measurements, we're always measuring the planet relative to the host star. And if the host star changes, that changes our interpretation of the planet. So let's look at some simulations I did a long time ago. This is some simulations here at the top of the spectrum of a star across Hubble's bandpass. And in blue is the simulated data. Um, Green is the data without any noise in it. And then red dashed lines or the red solid lines are if we add 3% star spots. So very, very small spot covering fraction of the star. What will happen is that when you inject star spots into your star's model, it changes how the star looks as a function of wavelength. So at this wavelength, it might look a little bit dimmer, but this wavelength, it might look a little bit brighter. And what this causes is it changes your signal of your planet itself. So if I have notionally a flat line due to a planet around an unspotted star, if I come back and observe that planet maybe a few months later, a few weeks later, when spots have evolved on that star's surface, that can drastically change the planet's spectrum for something that is notionally flat to something that is much larger or smaller, but also has some structure in it. And this structure can sometimes masquerade, for example, as water vapor or clouds or hazes. And while the planet might not have any of these things on its surface, we might wrongly think it does simply because we're making differential measurements with respect to the star. So again, since we're measuring planet relative to the star, if the star changes, that also impacts our interpretation of the planet itself. And this impact um, when we wrote this study at the time, it looked like we could basically continue to mostly ignore this method for Hubble, but this becomes an even larger issue for the James Webb Space Telescope. It has expanded wavelength coverage. It has a much larger primary mirror, from 2.4 meters on Hubble to 6.5 meters on James Webb. We have a significantly larger mirror, which means we have higher sensitivity measurements, higher signal to noise. So this small effect becomes that much more important to understand, to characterize, and then to remove. So let's look at some real data. Here's some observations in white of the exoplanet GJ486b. And then we can now try to fit this data taken with the James Webb Space Telescope by various models. So for example, we can actually fit this exoplanet's data with two different models. One, where you have an atmosphere of the planet here in blue that's water rich, but also what fits similarly well is purely a spotted star. And again, that's because the star's spots are so cool where you can actually have molecules such as water absorption that can masquerade as a false positive of water absorption in the planet. So the star is polluting our planet's signature and causing us to draw the wrong conclusions on the planet's atmosphere. So you can see, though, while these models overlap very well with the James Webb data, they diverge here at these shorter wavelengths. So we potentially, if we had coverage here from zero point 0.5 to 2.3 microns, we could distinguish between these two atmospheric models and then better understand if the James Webb data is coming from the planet or from the star. And that's exactly where Pandora comes into play. We're observing wavelengths from the visible to the near infrared. We're observing these stars as they vary in time. Their brightness changes in time due to flares, due to plages, due to star spots rotating in and out of the field of view. We'll be observing these planets over about a year and their host stars over a year. So we can actually observe in two dimensions how these stars impact their planetary signals. We'll be observing how the stars change in time. They might be more active now, and they might be less active in 6 months from now. And we can see the impact of that on the spectrum, the signature of the planet itself. And from that, what we can hopefully do is by characterizing this impact of stellar variability, we can more accurately determine what molecules are truly in the atmospheres of these planets, but also they'll give us insight on how to better characterize them and remove their false positives on things like James Webb. So again, we have this data that can be explained here by either a star model or a planetary atmospheric model. And Pandora will be giving us that wavelength coverage in the visible near IR to break that degeneracy. And by doing so, it'll help us better analyze James Webb Space data in the future. Um, but Pandora doesn't launch until the earliest of this fall, and Pandora only has about a 1 year mission lifetime. But there are lots of folks on the ground that have amazing setups or have internet access and have access to telescope data, such as through us at Exoplanet Watch, where you can help us characterize these exoplanet host stars. And small telescopes totally can help. Here's some data that we published back in 2020, where we looked at the scatter in data. So this is the precision of data. Lower is better, lower uncertainties, higher numbers are worse. And this is all from a single 6-inch telescope or a 10-centimeter telescope. And right here we have the uncertainty as a function of the host star magnitude. So over here are brighter stars, over here are dimmer stars. What we've been able to find is that a single 6-inch telescope can get precisions as high as 0.5% over 1 minute. So small ground-based telescopes can achieve very high precisions despite them being relatively small and from the ground. In addition, they can do very impactful transit science as well. So again, here we have host star brightness, dim stars, brighter stars. And then here is measuring the uncertainty of measuring a transit, that dip in brightness as a planet passes in front of its star. And we similarly found that a small 6-inch, 10-centimeter telescope can do very precise science, even by looking at the mid-transit times, predicting in the future by getting more accurate measurements today of when those transits were to occur. So by doing so, our citizen scientists through Exoplanet Watch can help us better predict when the next transit were to occur. And this is important for Pandora because we can then help Pandora better schedule when it observes these targets to make sure we're looking at them when those transit events were to occur. In addition, though, we can expand upon that long baseline monitoring of host star data. So let me get a good plot from here. So actually, one of my students at Arizona State University, Fred Nuger, he's been leading a group of students who have been observing Pandora targets. And a lot of our citizen scientists at Exoplanet Watch already have been observing exoplanet targets as well. So here's 9 observations by Fred and his students. And what they are seeing right here is you can see where the planet passes in front of the star, causing the star to appear to dim. And what they're able to do with this data is actually three different things. Well, really two different things, excuse me. They can help us refine these transit times. Again, measuring when the transit happens today to better to understand and predict when they happen in the future. But also they're able to use the data out of transit when you're observing the star alone to measure how the star changes with time. So what they're able to do is actually by looking at these transits and coming back and taking many repeat observations, they're able to measure stellar variability. So on these two plots, we have time versus the brightness of the star. And you can see there's maybe some structure here in this data. You know, the star might be getting brighter, then dimmer, then brighter, then dimmer, then brighter. It has cycles just like our own sun. Or perhaps there's star spots on the surface of these stars that are rotating in and out of the field of view over days. That may perform an analysis on that data And they've been able to figure out how to fold this data together to find those periodic signals of brightening and dimming or brightening and dimming of the star. And they can actually start to measure the rotation rates of these stars. We think that rotation rates of stars are correlated with their activity. Stars that rotate more quickly or have higher levels of convectivity potentially have higher stellar variability. So perhaps by measuring the rotation rate, we can help remove or characterize the stellar variability and remove it from the data. In addition, we can use this rotation information to better help really expand the capabilities of other exoplanet observations as well. So we're truly in that golden age of exoplanetary science. We've had missions like Hubble, Spitzer, Kepler, TESS, James Webb, Roman, Habitable Worlds Observatory, which is being designed right now. We have this amazing heritage by ground-based telescopes. European Space Agency has been launching many, many different very impactful missions like Kuro and Gaia and Cheops and Plato. Ariel will be launching this decade. We also have small satellites like Pandora that'll be launching potentially as soon as this fall. And while Pandora will be doing incredible science by itself to help expand upon the science capability of James Webb and future observatories, you have the opportunity today to help us by helping us observing Pandora targets, either with your own telescope or by using one of ours. So if you're interested in helping out, you can scan this QR code or go to this website, or you can just Google NASA Exoplanet Watch, and we should be one of the first things that pop up. On there, we have tutorials on our website on how to participate. You can check out data, but I also recommend that all of you sign up for our Slack channel as well, just like you do for Kilonova catchers, because just like with this project, there's lots of amazing, friendly people out there on Exoplanet Watch who are more than welcome and willing to help you out
Hello?
if you run into any issues. Yeah, go ahead.
I don't know. I just lost connection there for a second, so I wanted to make sure everyone could hear me still.
No worries.
Thank you so
So if you're
much. Go
interested,
ahead.
yeah. So if you're interested in joining Exoplanet Watch, feel free to scan that QR code or go to that website or Google NASA Exoplanet Watch, and we'll be happy to have you. And with that, thanks for your time, and I'm happy to answer any questions the remaining time. Yeah, John, go ahead. Hope you're muted.
I took the video off, but forgot that.
No worries.
IOTA has very specific requirements for telescopes and cameras. I know your range of telescopes has gone from 2.5 to whatever, but what about camera requirements?
We have none whatsoever. We have no requirements on the cameras. We have no requirements on the telescopes at all. Um, if
Just the
you
data.
just the data,
I
exactly.
assume
And
fits formats only.
so, yeah, we do any FITS formats because we need the information in the header files to analyze the data through our project. FITS make it a lot easier to operate with. There are also, I believe, some conversion tools online that can convert JPEGs and stuff like that into FITS files. But there's lots of free software online that you can use with existing cameras to make those FITS formats as well. If you already have a rig, I would recommend you give it a try first. I'm always a huge proponent of not spending money when it's not necessary. And if you give us the details of whatever equipment you might have, people can offer their help and advice on using them as well.
Thank you.
That's
Yeah,
awesome.
great
Thank you.
question. Yeah.
So KNC actually, with the help of its members, a few of them are here actually, have written a manual. So me and a few others of the members have written a manual that shows the different programs that our members use to make FITS files, to do photometry. And so I can send you that link in case any of your members might be interested in that.
That'd be great. Thank you.
Yeah. We do have a question in the chat from Eric Browens. What is used to analyze the light curves? Is it Batman?
Oh, we use light curve, I think is what we use instead. So we don't use Batman, we use a different uh light curve fitting. A
What
good
was the
question.
name
And
of it? So I
it's
missed it.
called, I think Pi Light Curve is what it's called. I'm blanking on the name, but if you go into our GitHub for Exotic, you can see all the Python packages that we import. I'm sorry, I'm forgetting. And thanks, Christine, appreciate it. And then I'm seeing that Michael is asking in the chat, do you have a preferred filter for the observations? We are filter agnostic. I recommend typically use the filter that gives you the highest SNR. So some folks, that's the R band. Some people don't have filters. Um, Again, the low-hanging fruit for Exoplanet Watch is the transit times, and the transit times are fairly agnostic of the filter that you use. So use whatever you have to get the data and the observations. Um, Occasionally, we will put out requests for filters, like for Pandora, for example, getting measurements of these host stars and their variability at a variety of wavelengths is helpful if possible. But if not, any data will be extremely helpful. We're in this phase of exoplanet science where we have thousands of targets and only so many observatories with capabilities. And there's so many incredible amateur astronomers out there that have their own rigs that rival what professionals use and have. So there's very much a large need for your help and a very clear niche that all of you can help out with. John, another question.
Now, follow up, what about exposure length?
Exposure length, whatever gets you the best SNR, quite honestly. So the micro observatory, for example, always uses 1 minute exposure times. Um, Really, it's just based upon your own rig and setup and experience. So if it's on the order of seconds, I wouldn't go much more than a few minutes, quite honestly, because then you sort of lose that temporal information of when the planet passes in front of the star. But typically, your observations are going to be like on the order of seconds, like tens of seconds to a minute or two. But again, it's use whatever that you think is going to get you the best SNR. You want to really do this on the order of minutes because the transits themselves are on the orders of about 1 to 3 to 4 hours typically. And then you observe for about 4 to 6 hours throughout the course of the night. So you can observe two full transits in any given night. We actually have one user out in Southern California who observes two transits a night. And there's also lots of amazing automation software out there that's completely free. So one of them packages is called Lina. We actually use it on our robotic telescopes out in Southern California. That's Nina. Completely free, runs on Windows and runs ASCOM devices, and it's incredible. Really love it. Yeah, Christina, go ahead.
It's so cool to hear from, hear from in your own words what exoplanets like and how similar it is to a lot of what KNC does. We co-author with our members, we do observations, except the triggerability part is different, but um, we are currently building a photometry tool for our members. But you seem to have taken a different route. You have taught them how to use specific photometry tools. And now, are these pipelines developed by yourself and other astrophysicists at Goddard, or is this something that was tailored for your members?
So this was originally built by us when I was back at JPL. So a bunch of astronomers and myself and software engineers and interns, a lot of amazing undergraduate interns. What they've done is they built this astronomy code that is based upon code that we were using as professional astronomers. And we got it to a point where we really liked it and we thought it was fairly user friendly. But then when we did a soft launch of the code online, it became very obvious that it was not very user-friendly at all. And lots of people had lots of issues with running it or installing it locally. Luckily, one of our users, Clay Talk, she's a high school teacher at Sanford Online High School. And she had this amazing idea that her students came up with of running this instead of locally on your own computer, you could run it on Google Colab. So you would no longer have to install Python or Python packages to get it running on your own computer. You still can if you want to, but quite honestly, once we launched that and spent a lot of time and effort on improving the user experience on the front end and having these tutorials and making things a lot more user friendly, I went from one, if not tens of issues a day on Exotic to maybe it's now once a week or once a month. It really changed things immensely. And again, the only real difference between any of you using this code and me using this as a professional astronomer is just the front end of how you interact and set up the code to run. But quite honestly, I've gotten to the point where I just use it myself as well. So there's really no distinguishing factors from how I use it versus how any of you might use it.
It's good to
Jean-Baptiste, yeah, yeah.
Colab is such a good tool. Yes, John.
You hear me?
Yep.
Thanks, Rob. Just a comment about Nina you mentioned.
Mhm.
Very useful plugin called Exoplanets, allowing to measure the convenient exposure time, say, like to 2/3 of saturation. This is very, very efficient. I recommend it very well.
That's a
Thanks.
great point. Yeah. So Nina has this amazing plugin. Not only helps you observe transits and make sequences to automatically observe transits. It's so simple that basically night to night we just hit a drop down list to select our target and we hit go. But we have on there, I like to do half well filling fractions of my pixels because I like to be conservative. But it really depends upon the linearity response of your pixels. So John, what you could do is you could look up, for example, the details, the schematics of your digital camera, and you can see when you continue linearity on your pixel response rate and expose up to that well filling fraction. I personally, I just like to be conservative. I usually hit for like 40 to 50%. That's just my own personal rule of thumb. But a lot of people can also expose up to 80% well filling fractions, as Jean-Baptiste mentioned as well. So Nina is an incredible tool and it'll do this for you. It'll take some test exposures and they'll say, oh, okay, here's the exposure time you need. It really makes things so much easier and automating so much easier. Thank you, Jean-Baptiste. Great point to bring up. Thank you.
Do we have any other questions?
And of course, if you remember any questions later, you can also just hop on our Exoplanet Watch Slack as well. It's linked to from our website, and you can ask us additional questions right there. And likely you'll get an answer from me almost immediately, or at least one of our members immediately as well. We have people across the world, so there's almost always someone awake that's willing to help out, or at least get back to you within a few minutes or hours. And it's just a friendly group of folks like you have here in this collaboration and community, and we'd love to have you as well. And Christina, we'll have to have you at our next Exoplanet Watch meeting so you can talk about KNC and get folks over at Exoplanet Watch involved in this too.
Oh yeah, I'd love to do that. I have been presenting a lot more, and John can attest to this. And uh, he made a comment last time that it's been interesting to see me evolve from like when I first started talking about KNC to now. And I like seeing I like hearing everybody's questions and hearing everybody get excited for it. And that's why I really wanted to bring you in here because I knew we'd have the same response of interest and intrigue.
He's a
But it's so good
seasoned
Yeah,
to
professional now, Rob.
see. Thank you.
yeah, and quite honestly, we as professional astronomers, we need your help. And there's only so many professional observatories that are out there. And as much as I want to use a Keck or a Gemini or a Magellan, 5, 6, 8 meter class telescopes, there's thousands of planets out there where those are just saturate those telescopes and they should really be used for other things that are harder to do. And that means there's hundreds, if not thousands, of targets that are really primed for small telescopes. And, these are happening in tens a night. And we need your help to observe these targets. So it's really great. I've been very lucky uh, to be able to work with other amazing citizen scientists such as yourselves and really the feedback, and I'm sure Christina in your experience as well, the feedback from your user group has really only positively impacted the project, and we've gone in so many positive directions that I never would have thought about if it not were for our participants, our watchers, for saying, hey, have you thought about doing it this way or adding this feature, this functionality? And it's been so much fun.
Absolutely. The input from you guys, from KNC members, has helped to bridge the gap between scientist and amateur astronomer. And I have been very much educated myself by interacting with you all. And it's made it easier to lead and to make decisions based on what you guys need and what you guys feel. And this is why it's so interesting to hear you, Rob, discuss like Google Colab and how that's working. I do have one more question about that. How
Yeah.
quickly, and you kind of touched on this, but how quickly did um, you get from saying, okay, your users want to do their own data analysis to getting it functioning, um, where you only have this 1 week, one issue a week problem.
Years, honestly, years, and in the long scheme of things. So we started coding up Exotic just before COVID, and then we launched it as a soft launch right around COVID happened that spring in 2020, and just kept on rolling it out from there. And while the back end we knew was working, we were really proud of how quickly it worked. Like it was one of the few codes that could take an entire data set and run through it in like 5 to 10 minutes and get science grade observations through it. um, the front end was very confusing and difficult for folks to work with and operate. And we were answering the same questions over and over again of how to get this installed, how to install the packages. And then with the collab, that just completely changed everything. And then we spent a lot of effort and time on really improving that front end experience there. And it's just a continuous iterative process. So, we're still adding new features and tweaking the code today. So while we've already gone through the entire microobservatory dataset once or twice now, because we keep on making changes and improvements to our code, it's important to re-reduce that data and to overturn it because your software might work better. But also it's really helpful to have multiple people analyzing the same group of data to ensure that you're getting the right answer. Because person A might use a different comparison star than person B, or person C might get a slightly better answer or a slightly newer version of Exotic or AIJ or whatever they want to use and might get a better answer. So it's really crowdsourcing this out there. And I think getting to another question you had, Christina, was the data analysis. That was actually one of my making the users be part of that data analysis was actually one of my goals from day one, is that I didn't want folks to um, sort of operate like a black box and lack that participation. I was very worried that if we didn't have users also analyzing their data or analyzing data from a robotic telescope, that we would lose that participatory science portion of the project and have our users feel disconnected from the science and the entire project as a whole. So by doing this, people have a lot more ownership of it, but it also enables us to expand to people that don't have their own telescopes. So right now we're actually building about 10 telescopes out in Southern California. 6 of them are online right now. We have four 6-inch celestrons, so four 10-centimeter celestrons, a zero 0.6 and a zero 0.4 meter that are observing every night. And then we're building another observatory of another four 6-inch celestrons, 10-centimeter celestrons as well. And there'll be 10 telescopes that'll be adding to our data checkout system so that anyone can participate in this project, even if you don't have the data.
That's awesome, Rob. Really, it is, and that's something that KNC is currently building towards now to have that
Awesome.
aspect of data analysis, and it's a little more tricky, obviously, because we're dealing with fast transients. So that is a lot of conversations are happening at the moment, especially to expand that user base, so that people who don't have, these 8-inch telescopes can still participate and the use of data and stuff like that. So it's really, really nice to see something like Exoplanet Watch be, harmonious and functioning. And I look forward to participating more now. And I also look forward to having another conversation with you because we're running out of time now. Just to kind of get some more introspective look about running a project like this and what that data analysis looks like and the use of data for everybody and how everybody interacts, because that'll be really helpful with, as Damien, who's the PI for KNC, and I start to really build onto these topics, especially since we've made such a huge stride with, we're now a NASA partner, we're getting our website up there, and we finished the manual, and so now we can get to the next step.
Awesome. Congratulations. Yeah, happy to continue chatting and yeah, help as
Wonderful.
much as I can.
Thank you.
I see
Oh, Michael Freeberg.
Big
Oh,
Heinz had a question as well. Yeah, I saw them raise their hand.
If there's still time.
yeah, we have 7 minutes.
Okay, cool. So I'm not sure whether I remember this correctly, but I think Exotic could be used like in live mode, where it ingests and plots data as it comes in
Yeah.
in plots that are not too crowded, so that you could use this in principle on an exoplanet star party event, kind of. Is this doable? I mean, would you
Yeah.
think
Yeah.
it's
So actually this is based on some code we actually wrote for ourselves because we would be at the observatory observing these transit events over 6 hours and we would get bored and we wouldn't be sure if we were actually observing the transit ourselves. So Kyle Pearson, really, he's one of the main brains behind Exotic, built up this code to do a very quick and dirty analysis of the data in real time so you can see the transit occurring. But theoretically, like you said, you could bring this to a star party and you could observe a transit and you can point to your laptop screen and tell someone that you're observing a planet passing in front of a star and casting a shadow all the way to the Earth, which is pretty cool. So we haven't, or someone hasn't used this function in a long time, but if you'd like to, please give it a shot and let us know how it works. And also, we'd love your help on it to make it work again if it doesn't.
Cool, thanks.
Yeah, I think
Thank
we'll
you.
create a channel in the KNC Slack for Exoplanet Watch if there's any events or stuff like that, since you invited me to talk about KNC events as well. So let's see about doing that. Wonderful.
Perfect.
Any more questions? Well, if not, thank you so much for coming. Thank you so much for giving this talk. It was wonderful, it was very insightful. And I'll make sure
Yeah.
to, when I post this on Forge, which is kind of like our database center for all of these webinars and telecons, that I'll include the links that I discussed, and I'll send you an email with a few of our links as well.
Perfect. Thank you again for having me, everyone. Really appreciate it. Hopefully see you on our Slack channel and continued luck and everything with KNC as well. Thanks again for having me.
Thank you so much.
Thanks, everyone. Have a good one.
Have a good day, KNC. Thank you guys for coming.
Thank you all.